This first session is about runtime systems. And the first talk is about multicore parallel runtime. It's by Steven Dolan, Leo, and Anil, if I remember well. And Steven will be giving the talk.
So yes, this is our attempt at a multicore OCaml. It's still a work in progress. Flipping ahead. So unfortunately, Emil and Leo aren't here because they're giving talks concurrently, which seems to be in keeping with the whole spirit of the thing. So I'm going to be describing this piece of work. So the first thing is I'd like to make the distinction between concurrency and parallelism. Concurrency is for writing programs. A concurrent program is one which must do several things at once. It has to handle lots of different connections from different clients. It has to respond to input from one channel while not blocking on another channel. Parallelism, as distinct from concurrency, is a performance hack. Parallelism is we can make the program go faster by running it on several cores. So it's important not to get the two confused. That's a major point we're trying to make. We shouldn't just think of having the same APIs for both parallelism and concurrency, but they're quite important to separate. So the current state of OCaml is that there are quite decent concurrency libraries. LWT and async give good support for concurrency. You do have to sort of wrap everything in monads, so this is somewhat limiting. It kind of infect the rest of your program. But it works quite well. They don't give any parallelism. Everything still runs on one core. It can respond to lots of different connections at the same time, but only on one core. There's also direct style threading libraries that don't involve wrapping everything up into monads. There's VM threads for bytecode and systhreads for the native code. But neither of those are scaled particularly well to very large numbers of concurrent requests. For parallelism in OCaml, the story is a little bit more sad. If you want to split into several Unix processes and communicate between those, there are quite good stories about that. You can use a parmap, net multicore, the async parallel library to split into separate processes, marshal the data out to some of them, do some computation parallel, and marshal it all back. So this works quite well if your data is quite small, splits up easily, and you don't have very much to send back. But if you're trying to do complicated message passing between large networks where many nodes are just taking a message and passing it on, and there's a lot of communication, then this approach leads to spending more of your time copying messages than actually doing any work. For actual just normal shared memory, running two things at the same time in the same program, there's not much at the moment in OCaml. So since concurrency and parallelism are broadly similar, why don't we just unify them? Why don't we just have the same API for doing something asynchronously? And the trouble is basically that the numbers are different. Concurrency, you have 10,000 concurrent things. You've a million different messages happening. You're routing thousands of messages or thousands of connections. Parallelism, you're running on a machine with 8 cores. So it's difficult to, if you're using the same APIs for both of these, like using, say, system threads as a concurrency mechanism, then you just end up in a mess of context switches. This is what you end up doing in Java or C# and so on, because those don't expose any sort of lightweight unit of concurrency. They only expose threads, the unit of parallelism. So this leads to a somewhat unpleasant programming model. So what we want to do is separate the concurrency and the parallelism tools, because there is no reason they should ever have been the same. For concurrency, we deal with fibers. Fibers are very lightweight user-space threads. They're very cheap to create. You can have millions of them at the same time. Domains are what we're calling the unit of parallelism. They're implemented as system threads. They're expensive to create. You generally create whatever number of them you want at startup and just leave them there for the entire runtime of the program. So you could have millions of fibers, but you'll only ever have 4, 8, whatever number of cores you have domains, and the fibers can be balanced across the domains. Since fibers are lightweight user space things, we don't have to deal with the overhead of kernel context switching. So we get similar to our async and LWT, where we get that sort of overhead of context switching, which is essentially zero. And domains give parallelism, but at a much coarser granularity. So the APIs for these kind of things, the concurrency primitives, look quite similar to LWT, async, concurrent classical. We're lacking monads, which is nice because we can actually, when we want to do this and then afterwards do that, we can use the semicolon for doing this rather than having to turn everything inside out through binds. So that this is an API for mvars, which is a basic concurrency primitive that you might know from LWT or concurrent classical or async or whatever. It's essentially a blocking variable. You can, it's a variable which is initially empty. You can put something into it and then it will be full. You can take something out of it and then it will be empty again. If you try to take something when it's not full yet, it'll block until it is in fact full and then take the value. So this is a useful primitive. You can implement lots of interesting stuff in this. And spawn just creates a new fiber by taking a unit-to-unit function and just doing it asynchronously in the background. So one useful primitive you can build out of this is just a general async function, which takes some work, just of type unit to alpha, and gives you back something of type unit to alpha. And the point is that the work is done asynchronously in the background. This is a simple implementation. There are better ones. The work is done asynchronously in the background, and eventually you can ask for the result. So you don't have to block on doing the work in order to wait for the results. You can just start doing it and wait for the result later on. So going to give a quick demo of what it's like to use these things. Is that readable? Okay, so here is a particularly stupid Fibonacci functions, because all work in functional programming must be demonstrated via the means of particularly stupid Fibonacci functions. So the stuff at the top here is just the implementation of the mvar API that was on the slide before. This is the actual interesting function. It's a stupid Fibonacci function. We call fib of n-2. We call fib of n-1. We do some work just for the sheer fun of it, so that we can test the garbage collector and see that it can actually handle getting rid of stuff that it doesn't need. And then we return a plus b. But the interesting thing here is, the first part of the Fibonacci work, we say, that may be done asynchronously. And then later on we say, after we do the second part of the work, and then we say, now we must wait for the result of the first part. So if we just run this on a single-threaded, so if you just run this single-threadedly, that's essentially as though async was just a complete no-op. This does a function call, gets the result, and returns. The point of this is that by using async there, we've told the system that it is allowed to do some of the Fibonacci work in parallel. Because this is all purely functional, and the thing being passed to async has no side effects and just returns a value, it doesn't matter whether or not it does it in parallel. Parallelism does not necessarily mean non-determinism. This is a completely deterministic program. It gets the same answer no matter what order the system chooses to run things in. So we run it on two domains, which is two system threads, and this spawns off another thread at startup, which attempts to steal work from the first thread. So the first thread is its call stack, except most of the things on that stack were created by asyncs. They were separate fibers. So the second thread looks over, sees that the first thread has this giant queue of stuff to do, and plucks some work off that and starts doing it itself and puts the result back when it's done. So we see when we run it in two domains, it goes approximately twice as fast, which is nice. So I was originally intending to give this demo on my laptop, and it would have had to stop right here, because my laptop has 2 cores, and going beyond that doesn't make it anything particularly interesting. But happily, this is over SSH to a much more interesting machine in the bowels of Cambridge, so we can keep turning this number out and see what happens. So when we run it on 4 domains, it goes, it's not quite 4 times faster, but it's close enough. If we run it on 10, it's close to 10x, but not quite. But happily this is a 40-something core machine, so we can just keep turning this up and see what happens. So yeah, we're getting diminishing returns there. Once we get to 48 cores, it's not going 48 times faster. I can't do the one with it looks like it's about 10 times faster. So yeah, we have lots of benchmarking to do, and lots of tuning and optimization and so on, to see what sort of speedos we can actually pull out of this. But at the moment, with a relatively simple work stealing system, it is in fact getting through the pile of work much faster than it would on one core.
Question?
Yeah.
When you spawn, you stop really spawning when you don't have enough domains anymore, or you keep spawning but then cheat?
Oh, so spawn, yes, spawn is not involving domains. Spawn is creating a new fiber, and it always just spawns them. A fiber has...
So there is a cost for creating a fiber if it's not useful because you don't have any more cores?
That's true, but creating a fiber is an allocation of the minor heap of about 30 words. So like these are... it has a cost, but the cost is like creating an array of size 30.
It's fine, I just wanted to know whether you were also tricky, smart to just avoid that.
Well, we just create all of the fibers and then we balance them. So actually, yeah, that would be mildly interesting. We can check that.
Can you manipulate the number of domain from the program?
Yes, actually. If you look here, this is actually manipulating the domains from the program. It just that camel domains is actually being read at the top of this file and spawning that number of domains.
Oh, okay.
So yeah, so to check what the actual overhead of these things are, we can just do this. So we won't spawn the domains this time because that won't help. So this is a completely single-threaded version. It's doing the same thing. So that was 3.528 instead of 3.559. So there is an overhead to creating fibers, but it's fairly minimal. Again, this is not a proper benchmark. We will provide actual numbers when we've actually tuned the system, provided we'll...
Also, you're using bytecode too.
Oh yes, sorry, this is all bytecode, by the way. I should have mentioned that earlier. So yeah, let's get back to this. Okay, so it works, but how? So yeah, this is what I was saying, that there's lots of fibers balanced over a much smaller number of domains. Creating a domain is quite a heavyweight operation. Creating fibers is cheap. OCaml currently has a minor heap for new allocations and a major heap for things that have hung around for a longer time. We've got basically the same design here. We've got one minor heap per domain and a shared major heap across all of the domains. So yeah, the design here is descendant of the Dolan collector from concurrent camel light, bringing the whole thing sort of full circle at this stage. So we're trying to make functional code go fast, because OCaml is good at making functional code go very fast. So immutability and symbolic processing goes, like what happens at one time is essentially exactly the same as what happens now. It doesn't involve any synchronization or any locking or anything for normal operations like that. Mutability in a parallel context is more complicated because the mutability is how different threads can actually interact. So we have to, there are some interesting details there which can make some programs run slower if they're using huge mutability, but hasn't seemed to be so bad so far, and we're just getting to the point of doing proper tuning and benchmarking, so we'll have a proper story about that sooner. So the way this works is there's a common shared heap across all the domains, and there are minor heaps per domain. So the idea is we want to make minor garbage collection, cleaning out those minor heaps, not have to involve any synchronization between domains. We want those to be totally independent. Because we do those quite frequently, and it's an OCaml program creates a large amount of garbage, and you want to get through it as quickly as possible. So the difference here from the Dolan collector is we allow those pointers from the shared heap to the minor heap. So the original design made sure there was none of those, which meant it was very easy to make sure that the minor garbage collections happened truly in parallel. For us, we allowed those because it turns out after the people doing concurrent Haskell and the multi-Milton team discovered this, that there's quite a cost in ensuring that there are never any pointers from the shared to the minor heap. You end up having to pull a lot of stuff up to the shared heap just because it might in theory be accessed by another thread. So what we're going for is we're allowing the pointers from a major heap to a minor heap. And we only do the same operation of hoisting shared data up to the shared heap, but we only do it when another thread actually tries to access the pointer. So when another thread actually tries to read something from a different domain's shared heap, they send a message to that domain copies that data and anything it points to up to the shared heap, and then returns new data. So this means that reads of mutable fields have an extra cost over what they do in single-threaded code. We only have to do this for mutable fields. Immutable fields can never point from the shared to the minor object, because an immutable object can only point to things older than it. But when you're reading a mutable field, you have to do an extra check to ensure that you're not trying to read a field from someone else's heap. If it turns out that this is what we're trying to do, then we send a message and copy all the data. So this means that since no thread is ever going to touch anything in your minor heap without politely asking you for it, this means we can still do completely independent minor collections. We never have to worry about another thread trying to access a piece of data in our minor heap while we're doing the minor collection, because we're just not going to process that request until we're done. For the shared heap, we're going for a mostly concurrent parallel collector along the lines of the very concurrent garbage collector from the Inferno project. So I'll say a little bit about how that works. Every object in the heap is either unmarked, marked, garbage, or free. Threads marking data are trying to turn things from unmarked to marked. So say that this object is still alive. When sweeping data, they're trying to turn things from garbage to free. And we've no real synchronization on any of this. Threads are racing to turn data from unmarked to marked, which is fine. If two threads, if there's a race condition and two threads mark the same object, then we just do slightly more work and everything is still fine. So then eventually when the threads verify that all of the data has been marked, they all synchronize and flip the meaning of these pointer bits. So all of the object all of the stuff which was previously labeled unmarked is now labeled garbage just by changing the interpretation of that flag. So for the C API, so the other, as well as maintaining compatibility with OCaml programs, you also want to maintain as much compatibility as possible with the C API because there's a lot of C bindings and stubs that use OCaml. We still have CAML inter-blocking section and CAML read-blocking section, if anyone's familiar with those, which are, with the current system's implementation, the only way of doing something in parallel. You enter a blocking section, it releases a giant block in the runtime, and then during that period, other threads can run. We still have the same, you still use those functions in the same way, but they have a different meaning now. What they mean is, this thread is blocked and isn't going to participate in GC. So a very long-running C call doesn't actually hold up anything else. Other domains can continue running, continue garbage collecting, even if one domain is stuck in doing something complicated in C. There are very few API changes that actually need to be made to port C bindings to the multicore system. Many of them are just very small syntactic things. We've actually managed to do most of them with sed, which is a terrible way to write programs. One of them in particular is our implementation of CAML modify needs to know the object being modified. So we can't do the usual pattern of taking the address of the field and passing that in. We have to pass the actual object in the index. But these are all totally trivial things. In particular, with the same atomicity guarantees as you currently have in OCaml, if there's lots of C bindings that relies on the fact that certain functions can never call the garbage collector, and those still work with our multicore implementation. The garbage collector might run, but it's never going to steal anything that you know about, because collecting garbage that you can see requires the cooperation of that thread. So if you're using functions that can never call the GC, then other threads might prepare to collect the garbage, but it won't actually be gone until you get to a GC point. So the current status of this thing is it bootstraps. It seems to work, although haven't been tested enough for me to actually say that with confidence. It installs with OCaml, but not very much else does, because unfortunately we branched this between 401 and 402. So caml p4 is broken, for instance. So next thing we need to do is just merge up to get us up to date with 402. The garbage collector needs lots of testing and tuning and benchmarking. In particular, the garbage collection policy, the decisions of when to do a GC are not made well at all at the moment. So we need to work on some good heuristics for when would be a good time to do GC and how much GC should be done at each point. Oh, and of course, this is just bytecode only at the moment. We started work on a native code implementation, but it's nowhere near ready to use yet. And a few other features are just broken at the moment because we just decided to leave them for later. Weak references, finalizers, and the like. So, questions?
Hi, it's great to see OCaml getting multicore support. So when you do garbage collection and you have the minor heap collection, how do you tell the root set?
So the roots, each domain represents a remembered set of the pointers from the shared heap to that domain's minor collection.
So when I mutate a pointer in the shared heap, I have to possibly modify the set?
Yeah, that's standard even for a single threaded collector. OCaml does that at the moment.
But this is a synchronization now that I have to do.
Oh no, sorry, it's not. There's a set remembered set for each domain, and they're totally single threaded. No domain needs to care about the other domain's remembered set, so they're just independent ones.
I'll ask you after. Thanks.
So, very nice work. Thanks. Thank you. I was wondering about databases when you have concurrent access to a mutable field. So do you need, in the end, are you exposing a weak hardware memory model, or are you kind of sticking with strong consistency, or anything in between?
So I think what we're settling on is enforcing ordering of stores, so that we can put on some platforms this will require putting a barrier into the into modifications, but those are relatively rare in OCaml compared to allocations and reads. So I think we're willing to accept some performance hit to expose a not insane memory model to the programmer. We have to be slightly careful because we can never have as weak a memory model as Java can, for instance, because when you allocate an object in Java, it comes back full of zeros, and you fill in the object and you push it in memory, and there's a race condition where other threads can see that it is full of zeros. But that's not an option for OCaml because we can't just say this is null. If I say I'm giving you a list, I can't just give you null and say I've done it. So we're going to have to do some work to enforce, I think Java people call it publication safety, where the writes to the object have happened before the object is published. And the easiest way to do that for us is just to put a memory fence, a store fence, into the modify code. So yeah, that's free on x86 because the memory model there is strong enough that this happens by default. But when we get around to porting this to ARM or PowerPC, which we'd definitely like to do, then this is going to have a performance impact, and I don't currently know how big that's going to be.
It sounded like your collector stops all of the mutated threads. Do you have a sense for whether it would be possible to have collection in parallel with mutators while maintaining the other nice properties that you've talked about?
Okay, so yeah, so it's a mostly concurrent collector, which means we do have collection in parallel, and we stop all the domains simultaneously at one point, essentially to verify that marking has completed. So the work that has to be done during there is a scan of the roots rather than a scan of the entire heap. It's not a big stop the world, do all the work collector. But we do have to stop all the domains simultaneously. So that's quite a big deal if you're in the land of Java, for instance, where you have confused concurrency and parallelism, and you may have 1,000 threads, but you'd have to stop all at once. We have separated fibers and threads, so the thing that we have very many of are fibers. So we have to stop all the domains, but that's going to be, the number of them is going to be approximately the number of cores in your system, so this isn't quite as big a disaster as it would be in Java.
So
very interesting work. I was wondering what happens in C bindings that use a pointer to a shared heap. How do you ensure that the garbage collector doesn't move that while the sync function is executing? Is there an equivalent of that giant lock that exists now?
No, so you have to do some things at the moment to ensure that doesn't happen. In single-threaded OCaml, you have to register it as a root. So you have to do exactly the same things in multicore. There's the code to ensure that happens is absolutely the same as in single core. The reason this works is because other domains can partially do the garbage collection in parallel, but because we have this synchronization point where all of the domains must verify the garbage collection is done before we can reuse memory, that means that we're not going to collect and reuse a piece of memory until every domain has said it's okay. And so the domain that's running that C binding will say it's okay when it knows what all the roots are.
Just trying to understand how the fibers work better. If a fiber does a blocking system call, does that block the entire domain?
So at the moment, yes. What we're going to do is implement set all the file descriptors non-blocking mode, have a big select loop, and when that happens, just pause the fiber, switch to something else, and do that until the select equal KQ, whatever it tells us that it's okay to keep running.
Right, although there are some system calls that you kind of can't get away with that with. Like, for example, file system calls.
So file, on systems that don't have good asynchronous file I/O, which is essentially all of them.
All of them, right.
We'll probably just have a separate C thread that does those calls in parallel and sends the result back to it, like over a pipe or something when it's done.
Right, I guess the one kind of warning about this is it's all very complicated. Figuring out how to deal with it and how to balance and how big your thread pool should be. It's an enormous pain, and it's the kind of thing that we've ended up solving at user level. And I'm at least a little bit nervous about the idea of solving it once and for all and unchangeably in the compiler. So I think some questions there as to how good of a job can you do, and can you do a good enough job with that so that people aren't really miserable with the things that don't quite work right.
Yeah, definitely. So we'll see what happens there. For the most part, we are trying to do as little work as possible in the runtime system because we're very lazy people, and try to expose primitives that allow different implementations of this as libraries. But yeah, it's an interesting problem.
A question about the higher-level programming interface to that. So at the beginning, you mentioned that so the current models, like async or AWT, create these monas which are a bit awkward. Well, I like monas, but the question is more, what you are doing in the low level, that it can be used by the higher level design, so that programs that use those monas get automatic parallelization, right? Or is something?
It would technically be possible for us to do that, but I don't think it's a good idea because there's a lot of code using LWT and async and so on that assumes that they're not running in parallel.
Yeah, but well, even if it's not using the same primitives, the same model where you model your effects and encapsulated in monas, you basically at the high level of the program specify what is going to run asynchronously, then that can be implemented on top of your primitives to get that sort of for free, right?
Yeah, we could.
Can I just pass in? So one thing you could do with async, for example, is you could effectively run multiple async schedulers.
Yeah, exactly.
Do roughly what Stephen was just talking about with sort of select loop or similar.
Yeah, that's something different.
And then things within that world are single threaded, which is nice sometimes for exclusion guarantees between bits of your code, but you allow that to run in parallel with the other worlds. So I think that's actually probably quite easy.
Yeah, but I think if we would like to run existing async and LWT code in this, but it would be more interesting to run several copies of it to handle several requests in parallel rather than to magically parallelize existing code, because that's often a disaster.
Yeah, well, I think it was going towards the Erlang model where you specify that's your different concurrency jobs, which are independent, and then the runtime just figures out how to run that in the course.
Okay, pretty nice work. I like to see this kind of things moving on. Just a little question. I'd love to use your building blocks as a kind of assembler for building parallel system on top of them, like skeletons or something like this. One thing that I didn't see that I would like to see is some primitive that allows me to say a particular fiber goes together with another set of particular fibers. I want to be sure this set of fibers are on the same domain, for example, or not on the same domain. Just to follow on, for example, what Jeroen was mentioning, if I have sensitive code that should not stop, I don't want this particular code to be in the same domain which is doing some blocking operation or something like this. Are you going to provide this kind of interface or primitive or directive or whatever?
Yes, so we're just starting to do interesting stuff for designing the high-level programming model. So far it's just been low-level details of a garbage collector that we're trying to make work. So yeah, what I showed there was a very primitive interface. There's lots of things that would be fun to provide to the programmer, priorities or affinity to domains and so on.
I do suggest you add this feature anyway, and we are all waiting for the native code generator.
We don't have time for more questions. Sorry. No more? One small question. Can you elaborate what happens when system decides on this synchronization point and some thread is running C binding inside this camel enter blocking section? So all the threads wait for this C binding thread to finish. So we just ignore that thread and continue with the collection.
So yeah, so there's a lock for each domain, which is ordinarily held by that domain, and no one ever even looks at that lock. When a domain is in camel enter blocking section, it releases that lock. Just this is a private lock for that domain, and the leave blocking section requires that lock. If another domain wants to do something which requires synchronizing with the domain that's currently blocked in the C API call, like doing the ending of garbage collector cycle, then if that domain is in the C blocking section, it will acquire that domain's lock and then do its share of the work and leave that other domain blocked in the C call.